In this lesson, we're going to go over another way to use U substitution. In this way, we're going to be using it on definite integrals. So in the last lesson, we used U substitution with indefinite integrals. So now we're going to look at it with definite integrals. So how would we evaluate this definite integral using substitution? So there are two methods you could use, and I'm going to show you both, and then I'll tell you which one is usually preferred by people and kind of used the most often. So you should know how to do both, but generally you can choose which one you want to do. So the first method is to, I'm just going to write it out here, evaluate the indefinite integral first, then use the fundamental theorem of calculus part 2. So basically what we've done before, find the antiderivative and then plug in your limits of integration. So let's try this one. So we've got the integral from 0 to 4 of the square root of 2x plus 1 dx. Okay, so we have to use U substitution here. So remember that U will be our innermost function. So in this case, our U is going to be 2x plus 1, and our du is going to be 2 dx. So we can see that we have a dx, but we don't have a 2 dx. So remember what we need to do is divide by 2. So what I really have here, I have the 1/2 that I can pull outside. That's coming from the dividing this 2 dx by 2. So I get 1/2 du. The 1/2 on the outside, the integral from 0 to 4, and then I have the square root of u du. And I'm just going to rewrite this. So we have 1/2 the integral from 0 to 4 of u to the 1/2 du, right? Because square root of u and u to the 1/2 are the same thing. So now we're going to use the reverse power rule to find the antiderivative of this u to the 1/2. So we have the 1/2 that's on the outside from before, and then we're going to take the antiderivative of u to the 1/2, so that will increase the exponent by 1, which would become 3/2, and then we're going to divide that by the 1 in front. So that's going to be 2/3 u to the 3/2. So I'm just going to multiply the 1/2 and 2/3. So I'm going to get 1/3 u to the 3/2. And I need to replace the u with my expression that I said that u was. So let's make this 1/3. Now instead of u, I'm going to put in this 2x plus 1 to the 3/2. And then this is what I'm going to evaluate from 0 to 4. Okay, so it's the same idea that we did last class, where you're identifying what u is, replacing u in the equation, and then putting the expression for u back in. The difference here is that we're not leaving our answer as an expression with a plus c. What we're doing is actually solving to get a number, since this is a definite integral. So now I'm going to plug in the 4, and I'm going to plug in the 0. So I'm going to get 1/3. So if I plug in 4, 2 times 4 is going to give me 8 plus 1 is 9. So I'm just going to put the 9 there to the 3/2 minus 1/3. I'm going to plug in 0 here. So 2 times 0 is 0 plus 1 is 1 to the 3/2. So technically we could leave something like this as our answer, since we've shown that we've plugged in our limits of integration. But I'm going to go ahead and solve this a little bit more. So I'm going to get 1/3 times 27 minus 1/3 times 1, which gives me 1/3 times 27 minus 1, which is 1/3 of 26. Sorry, I'm going off the page here. So that is going to be 26/3. Okay, so that would be our final answer, and that's simplified. Okay, so this was method 1, just doing what we did last class and identifying what u is, plugging the u in, and then changing the expression again by plugging the original expression back in for u, and then identifying what the values are when you evaluate it at the limits of integration. Method 2 is the one that's usually preferred. And with method 2, what we're doing is we're changing our limits of integration. So whereas method 1, we changed it to u and then we changed it back to x, we're going to keep everything in terms of u, and we're going to change our limits of integration from x's to u's. So hang on one second. So our second method, which is the one that I just said was more preferred, here's the steps. I'll just write this out here. So we're going to find new limits of integration. So let's look at this. So I can identify what u is going to be from this problem, right? It's the same problem as before. So my u is going to be my innermost function. So u is going to be 2x plus 1, and du, again, is going to be 2 dx. So my limits of integration right now are 0 and 4, and that is in terms of the function having x's in them. So if I want to change them in terms of what u would be equal to, what I'm going to do is say, over here, when x is equal to 0, right, because that's my lower limit is 0. So when x is equal to 0, u is going to equal, I'm going to plug in 0 for x in my u equation. So u is going to be 2 times 0 plus 1. So that means that this u value is going to be equal to 1. Then when x is equal to 4, u is going to be 2 times 4 plus 1, which is going to be u is equal to 9. And you might notice that these values of 1 and 9, we use them in the previous method, but at a later point. Okay, so what we're going to do here is rewrite this problem. So the original problem, I'm just going to write this like this, was 0 to 4 of the square root of 2x plus 1 dx. But what I'm going to do is change this. So I'm really going to have, I'm going to pull out the 1/2 since I don't have the 2 dx. So instead of 0, I'm going to use 1 as my lower limit. And then instead of 4, I'm going to use 9 as my upper limit. And then I have the square root of u du. So the difference in this way is that when I take my antiderivative, I'm not going to put the u expression back in. So let's keep going from here. So we're going to get 1/2. And just like before, we're going to take the antiderivative of the square root of u, which is u to the 1/2. So when I take the antiderivative, I get 2/3 u to the 3/2, which is exactly what we did before. Again, I'm going to multiply 1/2 times 2/3, so I get 1/3 u to the 3/2. So the difference here is that I'm not plugging in 2x plus 1 in place of u. I'm just going to take this expression in terms of u and plug in my new limits of 1 and 9. So we're going to get 1/3. So I plug in 9 first. So this is going to, I'm just going to pull the 1/3 out from everything since that's what's in common. So I have 9 to the 3/2 minus 1 to the 3/2. And when I simplify this, I get 26/3, which is the same exact answer I got before. And I'm just going to go back real quick to show you again. So method 1, we kept the limits of integration as they were. Once we found the antiderivative, we had to replace u with the original expression and then plug in those original limits of integration. In method 2, we change the limits of integration in terms of u. So we take what they were in terms of x, we plug them into the u expression and change those limits of integration. And then when we take the antiderivative, we don't need to plug the u expression back in because now everything is in terms of u. So we plug in our limits of integration that are again in terms of u and get the same answer. So in method 1, we're using everything in terms of x, even though we're using u as kind of an in-between piece. And in method 2, we're just changing everything to u's and using u all the way through. Hopefully that wasn't too confusing. So let's look at another example. So when I do these examples going forward, I am going to use method 2. If you prefer method 1, by all means, use method 1. So for method 2 in this one, I'm going to identify u as my inner function, which is 3 minus 5x. So du is going to be negative 5 dx. And I don't have a negative 5 with the dx. I only have a dx. So I have to pull out that negative 1/5. So negative 1/5 is going to come out. I'm going to change my bounds. So when x is equal to 1, u is going to equal 3 minus 5 times 1, which is negative 2. When x is equal to 2, u is going to equal 3 minus 5 times 2, which is negative 7. So now my limits of integration went from 1 to 2 to negative 2 to negative 7. And then we have 1 over u squared du. Okay, now we notice a problem here because our limits of integration are not in the correct order. Our lower limit should always be the smaller number, and the upper limit should always be the larger number. So we have to flip this, and remember, when we flip the limits of integration, we are negating the sign on the outside. So we're going to make this negative, so a negative negative makes this a positive 1/5. And then we have the negative 7 on the bottom and the negative 2 on the top. And I'm just going to rewrite 1 over u squared as u to the negative 2 du, just to make it easier to do the reverse power rule. So now I'm going to take the antiderivative of u to the negative 2, so that 1/5 is on the outside, increase the exponent by 1 to get negative 1, and then divide it in front. So I'm just going to say multiplied by negative u to the negative 1. And I'm going to keep it in terms of u since I changed the bounds. And now I'm going to evaluate it from negative 7 to negative 2. So I get 1/5 times, if I plug in negative 2 first, this is going to give me negative 1 over negative 2, which is just 1/2. And then I'm going to subtract, plugging in the negative 7. So that's going to give me negative 1 over negative 7. So let me just clean this up a little bit. So 1/5, we get 1/2 minus 1/7, which gives us, common denominator here of 14 is going to give us 5 over 14. So we end up simplifying this to be 1 over 14. Okay, so let's look at this next one. So u, now it's hard maybe to figure out what the inner function should be and what the outer function is when it's written like that. But we want to see if we see the derivative of something in here. So since I have this x on the bottom, right, this is going to be the same thing as the ln of x times 1 over x dx, just kind of rewriting that a little bit. And I know that the derivative of ln x is 1 over x. So my u should be ln x. So once we figure out if we see a derivative in the problem, the other one then is going to be the u. So my u is ln x, my du is going to be 1 over x dx. And I have all of that, so I don't have to pull anything out. So I'm going to change my bounds. So when x is equal to 1, u is going to equal the ln of 1, which is 0. When x is equal to e, u is going to be the ln of e, which is 1. So we're going to change our bounds from 1 to e to 0 to 1. And then what we have inside is just u du. Since u is ln x and we have that times du, we just have u du. So now we just take the antiderivative of u, so add 1 to get 2, and then divide it, so 1/2 u squared, and plug in our limits of integration. So if you notice in the last couple examples, because the 1/2 is the constant and it's going to be part of both pieces when I subtract them, I'm just pulling that outside. So now I plug in the 1, so I just get 1 minus 0. So this is going to give me 1/2. Okay, so again, let's identify u. U should be my inner function, so x cubed plus 1. My du should be 3x squared dx. So I notice I do have the x squared dx, but I don't have the 3, so I'm going to have to divide it. So I'm going to do 1/3 on the outside first. Now I'm going to change my limits of integration. So when x is equal to 0, u is going to equal 0 cubed plus 1, so that's 1. When x is equal to 2, I'm going to end up with a u equaling 2 cubed plus 1, which is 9. So my limits of integration are now 1 and 9. And now I have the square root of u du. So again, I like to kind of see it as u to the 1/2. It makes it easier for me, at least, to figure out the antiderivative. So similar kind of to before, because we had ones like this, the 1/3 on the outside. This is going to be 2/3 u to the 3/2. And I'm just going to multiply that, and this is going to give us 2/9 u to the 3/2. And I'm using those new limits of integration. And then I'm going to pull out that 2/9 because that is the constant. When I plug in 9, I'm going to get 9 to the 3/2 minus 1 to the 3/2. So this is going to be 2/9 times 27 minus 1. So we're going to get 2/9 times 26, which will give us 52/9. All right, and then we'll do one more for good measure here and look at this trig one. So we have a lot of things going on here, but again, we want to notice, do we see a derivative in here as well? So I have this tan cubed theta secant squared theta. I know that secant squared is the derivative of tan, so I'm going to say that u is tan theta, and du is going to be secant squared theta d theta. Okay, so I have the secant squared theta d theta. I don't have anything else that's I have to divide out, so I'm going to leave it like that. I am going to change my bounds. But before I do that, let me just rewrite this. So when I have this tan cubed, remember that that's the same thing as saying tan of theta quantity cubed, which is another way of writing it. So when we go to replace the stuff with u, we'll be able to see that it's going to be u to the 3rd. We'll come back to that. So let's change our limits of integration. So if x is equal to 0, u is going to be the tan of 0, which is 0. And when x is equal to pi over 4, u is going to equal the tan of pi over 4, which is 1. So now we have the integral from 0 to 1 of u cubed du. So take the antiderivative of u cubed, so that's going to be 1/4 u to the 4th. And then we're going to plug in our limits of integration, and we end up with 1/4 as our final answer.